Namaste and welcome to the lecture on linear algebra through geometry. In the past few lectures we have been looking at vector spaces, we have looked at vector subspaces, and then we looked at the linear independence of vectors, then we looked at the span of a set of vectors, then we looked at basis, and we looked at the dimension of a vector space. We said that the dimension of the vector space is basically the number of elements in a given basis, and we said that every basis for a vector space has the same number of elements, and therefore that becomes the dimension of your vector space or vector subspace. And then we moved on to look at the subspaces associated with the matrix. Suppose we had a real matrix A, m by n matrix, and we said that there are certain subspaces associated with these with this particular matrix A, and one of them that we found in the last class was the null space of a matrix. So, the null space of the matrix, if you recollect, it is basically the set of the solutions to the homogeneous system of equations, say Ax equal to 0, and we found out that from our earlier knowledge of let us say vector spaces and vector subspaces, which we knew that okay, if any line passing through the origin is a vector subspace, any plane passing through the origin is a vector subspace, and the 0 vector alone was a vector subspace. We looked at all that, and from that knowledge whatever we gained, we looked at the solution to the homogeneous system of equations. We took some examples and we figured out that yes, indeed, like we have the system of equations, the homogeneous system of equations, indeed it can have only the trivial solution to be the solution, in which case the subspace associated, that the set of solutions is just going to be the trivial solution, and we already know that the trivial solution which is basically the 0 vector that you are going to get, that 0 vector by itself is a vector space, and we said that look, so that is going to be the subspace. So that is a subspace that we had. So one more thing, and that we saw that if you have a square matrix A, we already know from our earlier knowledge of the matrix inversion and stuff that if a square matrix, if you have a system of equations where you have n equations and n variables, and you look at Ax is equal to 0, if x is equal to 0 is the only solution to this, we said that the matrix is invertible. We know that idea, and in such cases we just had the unique solution to be x is equal to 0, which is the trivial solution, and in that case we found that the null space is basically just the 0 vector, the set containing the 0 vector. Then we moved on to a second example where we looked at system of 2 equations in 2 unknowns in 2 dimension. We said that the solution to that system of equation was basically your what we call a line passing through the origin. So we had that, we saw that it was a line passing through the origin as in this case, and we already know that a line passing through the origin is basically vector subspace, and we found that here also the set of solutions to the homogeneous system of equation is indeed what you call a subspace. And we looked at very many other examples. We slowly we went off to 3 dimension, and we figured out that okay, in this example we figured out that the null space is basically again a line passing through the origin. We figured out that the system of solution to the system of equations in a homogeneous system of equations in this case was basically a plane as given here. The set of all those vectors which are in this plane will actually be a solution to this system of homogeneous equation, and therefore, and this is a plane which passes through the origin. So we said that again the null space for this particular system of homogeneous equation is, homogeneous system of equations was basically a plane passing through the origin. And so we went on with many other examples where we even considered matrices which are not square. We were looking at rectangular matrices. For example, we took a tall matrix here as in this case where we had A which was this matrix, and then we had a fat matrix here or a wide matrix here where we have this matrix A, and in one case we figured out that the matrix A was basically a transformation applied on 2 dimensional vectors. So, we were basically looking at the set of those 2 dimensional vectors or 2 component vectors which get mapped to the origin in 3D space or origin the 0 vector in R3, and here we figured out that there is only one vector 0 which was getting mapped to the 0 vector on the right hand side. And in this case where we had a wide matrix or a fat matrix that we say, we figured out that this has basically another line passing through the origin to be the null space of this. So, what do we understand from here? We generalize this result and we say that the set of solutions to Ax is equal to 0 will actually form a subspace of this vector space Rn, right, because this matrix A is going to transform n component vector to an m component vector, and therefore we say that if you look at the null space is basically the set of the n component vectors which get mapped to the m component 0 vector, and therefore null space is a subspace of A, right. We figured that out. Now, what we do in this class today's lecture is basically we are going to look at something more. Now, what we do is, let us look at this. Consider this Ax is equal to B. We are going to look at Ax is equal to B, and what is it that we are going to look for here. So, assume that A is basically m by n matrix. So, it is an element of this R m by n, it is an m by n matrix. So, this A is going to transform an n component vector and to give a B vector which is basically an m component vector. So, I will write this as R m. Yeah. Now, when I say Ax is equal to B, what does it actually mean? So, let us look at that. So, if I say Ax is equal to B, let A be equal to A11, A12, A13, etc., A1n, and it goes like this. So, I have AM1, AM2, etc., AMN, and my x is going to be a vector from Rn. So, that is going to be of the form x1, x2, etc., xn, and I am going to have my B vector which is going to be an element of Rm, and that is going to be of this form B1, B2, etc., Bm. This is what we have, right. Now, the question is, if you look at the column picture of this system of equation like Ax is equal to B, what it says is the first component of this x vector, we have already seen the first component of the x vector is always going to scale the first column vector of the matrix A. So, this Ax equal to B now can be this is basically expressed as x1 into the first column vector of the matrix A. I will call this as A1, I will call this as A2, and let me call this as An. So, A1 plus x2 into A2, therefore, what happens is our x, the solution to the system of equations Ax equal to B that we are looking for, I mean the values of x, that becomes the scaling factor for each of these column vectors that we have for the matrix A, right. So, we have plus etc. xn, An, and what we are saying is this is going to be equal to the vector B. Now, what does that mean? That means we want to check, we want to find out scalars x1, x2, xn such that B can be written as a linear combinations of the columns of A, is that right. So, we want scalars. So, to solve Ax equal to B in this case implies to solve Ax equal to B means find scalars x1, x2, xn, x1, x2, etc., xn such that the B vector can be written such that B can be expressed as linear combinations of the columns of A. as linear combinations of columns of A. Now what does that mean? That is exactly what we have written here, that is B is equal to x1 A1 plus x2 A2 plus etc. plus xn an. Now here we have a question. There are two things that can happen. What is it that can happen? One, okay, let's take two cases arise here. Two cases arise. What is the first case? The first case is that we can actually find scalars x1, we can find scalars x1, x2 etc. xn such that the vector B can be written as x1 A1 plus x2 A2 plus etc. plus xn an. The second case is interesting. What is that? We cannot, there exists no scalars. There exists no scalars x1, x2, xn, x1, x2 etc. xn such that B is equal to x1 A1 plus etc. plus xn an, right. This is what it is. Now let us look at what actually happens to the set of B's that I can look at. Okay, let us look at this. Let us assume, let us look at the case 1 first of all. So case 1 where we can find there exist scalars x1, x2, xn such that B is equal to x1 A1 plus etc. plus xn an, right. Now this clearly says that B can be expressed as a linear combination of the set of the column vectors of the column vectors, basically where the column vectors, the vectors are A1 an, A1 A2 an are basically the columns of the matrix A. This means B can be expressed as linear combinations of the columns of A. The matrix A, right. Now let us ask this question. I want to look at the set of all possible B vectors which can be expressed as linear combinations of the columns of A. So what are we looking at? We are going to look at the set of all possible B vectors, that can be written as, that are okay, set of all possible B vectors that can be expressed as B is equal to sigma xi ai, I is equal to 1 to n, right. I want to look at this collection of all possible B vectors. Note that the B vectors actually are in, they are basically m component vectors, they are elements of Rm. So note that B is an element of Rm, is that clear. So B, the B vector is basically an element of Rm. So let us do this, right. That means AIs are basically m component vectors that we have. Now I want to look at this set and see whether there is something interesting that happens with this set, is that clear. So what do we want to do? First of all, let us see, let us check. So let us probably call this set of the set of all possible B vectors, let us call this set, let this set be called as I will put this name RA. I want to look at this as RA, let this set be RA, that means the collection of all possible B vectors I am going to denote it as RA. So now the question that we have is, you remember when we had the idea of a subspace of a vector space, we had 3 properties for the subspace to obey. What is that? The subspace, basically the subspace of a vector space must actually be what do you call a vector space in itself under the operations which are defined in the vector space, right. So basically we were looking for closure under vector addition, closure under scalar multiplication, and we must have this 0 vector to be present. If these 3 hold good, then we say that the set of vectors that we are looking at, the subset of vectors from a vector space is going to be a subspace, right. So now we want to check if RA, so let us check if RA is non-empty. So is RA non-empty, that means, so the question that we have is RA non-empty. What does that mean? We just want to check if this set of vectors, we have at least one vector in this set which can be expressed as a linear combination of columns of A. Of course we do have, the thing is the m component 0 vector is already there, because that can be expressed as the linear combination of the columns of A, yes. So the m component 0 vector, so the 0 vector which let me say which is in Rm, so let me call this as the 0 vector, is an element of Ra. Therefore Ra is non-empty. So the answer to this question, the answer is yes, Ra is non-empty. Now let us look at this collection Ra, assume that we have vectors which can be expressed as linear combination of the columns of A. So let us look at this, let U and V be such that the vector U, let me make that let U V be elements of Rm, let me write that. So let U comma V be elements of Rm be such that I am going to write U as basically I am since and let me say that let me do this. So let U comma V elements of Rm be elements of Ra. Right. There are 2 vectors U and V which are elements of Ra. What does that mean? I can write this vector U as, let us say, alpha 1 A1 plus alpha 2 A2 plus etc plus alpha n An for some real scalars, alpha 1 to alpha n. Okay. The moment I say U is in Ra, it simply means U can be expressed as linear combination of the columns of the matrix A. Similarly, let us take the vector V. So V is also a vector which is nothing but, let us say, beta 1 A1 plus beta 2 A2 plus etc plus beta n An. Because V is also an element of this Ra, what we are going to say is V can also be expressed as some other linear combination, let us say beta 1 A1 plus beta 2 A2 plus beta n An, that means for some other scalars. So, for some real scalars let us say beta 1 beta 2 etc beta n. Yeah. Now, let us take this as equation 1, let us take this as equation 2. Now, what am I going to do? Let me add 1 plus 2. So, what do we get? We get u plus v, right. I add these two vectors u plus v, which is nothing but u1 u2 etc um plus v1 v2 etc vm, which is nothing but u1 plus v1 u2 plus v2 etc um plus vm, right. That is what I am going to get. This is on the left hand side. Now, if you look at the right hand side, so what do we get? Let us do this. So, what we have u plus v is equal to, we had alpha 1 a1 plus alpha 2 a2 plus etc plus alpha n a n, that is basically my u vector, and then plus beta 1 a1 plus beta 2 a2 plus etc plus beta n a n, right. This is, that is basically the b vector. So, what am I going to get here? I am going to get this as alpha 1 plus beta 1 into a1 plus alpha 2 plus beta 2 into a2 plus etc plus alpha n plus beta n into a n, right. Now, and what was it on the left hand side? This was basically equal to u plus v, which was basically given by u1 plus v1 etc um plus vm. That means u plus v was giving me another m component vector, let us say, let us call this as w, let us call that vector as w. So, what do we have? We have this w vector, which is an m component vector, which can actually be expressed. Now, alpha 1 is a scalar, beta 1 is a scalar. Now, you add these two, I get another real number, let me call that as gamma 1 a1 plus gamma 2 a2 plus etc plus gamma n a n. I am going to call this as, let us say, gamma 1, call this as gamma 2 etc, call this as gamma n. Now, what did we find? We found something very interesting. What is that? We found another vector w, which is again expressed as a linear combination of the columns of the matrix A, which means this w vector, which is also, it also belongs to R A. Now, u was an element of R A, v is an element of R A. Now, what we see, because w, which is actually the sum of u plus u and v, w was the vector which was resulting from the addition of those two vectors u and v, even that is expressed as a linear combination of the columns of A, which means the vector w, which is actually u plus v, is also an element of R A. So, this implies w vector, which is equal to u plus v, is an element of R A. Why? Because w can be expressed as, because the reason is here, w can be expressed as linear combination of this. That means the set R A is closed under vector addition. So, I am going to say R A is closed under vector addition. Yeah. The vector R A is closed under, I mean the set R A is closed under vector addition. Now, what are we going to do? We are just, so this actually makes us a bit curious, because the set is non-empty and the set is closed under vector addition. Now, what we do is, let us check whether this set is going to be closed under scalar multiplication. If all these three happens, then the set R A qualifies to be a subspace of R M. So, that is what we are going to look at. So, what we do is, let us look at the third one. So, what do we want to do? we want to look at the same vector, let us say u. So, the vector u can be expressed as let us say alpha 1 a 1 plus alpha 2 a 2 plus etcetera alpha n a n, right. Now, what I do, I take a scalar multiple of this vector u, let us call this let C 1, okay, let C be a real scalar Now, what we want to do, we want to check if this, and then I look at the scalar multiple of u, okay. So, what is C u? C u is another vector which is going to be say C 1 u 1 etcetera C m u m. Now, that is nothing but C times this alpha 1 a 1 plus alpha 2 a 2 plus alpha n a n, is that right. Now, I can write this as C times alpha 1 into a 1 plus C times alpha 2 into a 2 plus etcetera plus C times alpha n a n. Now, if you look at this, C is a scalar, alpha 1 is another scalar. So, let me put this as say some other, let us say k 1. So, this is going to be k 1, this is k 1. So, I am going to write this as k 1 a 1 plus k 2 a 2 plus etcetera plus k n a n, which means what we find is this set R A, this C u, the scalar multiple of this vector can also be expressed as a linear combination of the columns of A, right, which means now the set R A, therefore C u is a linear combination of columns of A. Scalar multiple of that vector is also expressed as a linear combination of the columns of A, which means the set R A is closed under scalar multiplication. So, what do we see? We see that the set R A being non-empty, closed under vector addition and under scalar multiplication now qualifies to be a vector subspace of R m. So, that if therefore, what we say is we say R A is non-empty, closed under addition, non-empty, closed under vector addition, and scalar multiplication. And closed under scalar multiplication, hence R A is a subspace of R n, it is a subspace of R m, right, because R A contained the set of all those B vectors which can be expressed as a linear combination of the columns of A, and that is what we call as I mean that is a subspace of R m. We have a name for this. So, R A is basically called the range of A, or it is also known as the column space of A, column space of A. So, R A is also the column space of A. So, what is interesting, when we looked at the subspaces associated with a given matrix, we figured out something interesting. On the R n side, we had the null space to be associated with the null space to be the subspace associated with the matrix A, and on the R m side, that means on the m dimensional space, we figured out that we have a subspace associated with the matrix which is called the column space of A, is that right. So, if I were to take let us say R m, if I take R n and if I take R m, I have the following. So, what is it that we have? On the R n side we have the null space of A this is basically the subspace of Rm, subspace of Rn. Okay. And how did we define this? Null space is nothing but the set of all vectors in Rn such that Ax is equal to 0. This is basically m component vector. And on the Rm side, what did we have? We had this, we had the range of A or column space of A, which is nothing but it is a subspace of Rm. So, what are we looking for? We are basically looking for Ra to be the set of all those B vectors which are in Rm such that B can be written as the linear combinations of columns of A, xi, ai, I is equal to 1 to n, which is the same as saying B is equal to Ax. Now, in the previous case, when we looked at the idea of null space, when we looked at null space, we did something interesting. We went from the solutions and we looked at the geometry of the solutions that we had for the homogeneous system of equations, and then we actually looked at the geometry. We said that the geometry is basically either the single vector, I mean that is the single solution or the single point 0 comma 0, the vector 0 vector, the set containing the 0 vector, or it is basically a line passing through the origin, or it is basically a plane passing through the origin, or geometry and that means in a higher dimensional space. We looked at all that, and then we said that okay, we know that any line passing through the origin or plane passing through the origin or the set containing the origin alone is going to be a vector subspace, and we found that out. Whereas in this case what we did is we mathematically proved that the set of B vectors which can be expressed as the linear combinations of the columns of A indeed qualify to be a vector space. That means now what we need to do is we need to check geometrically whether this holds good. There we went from geometry to the proof, and now what we are going to do is we are going to look at from this proof let us see the geometry of this vector spaces. So, the agenda for the next lecture would be the geometry of the column space of A. How is it going to look like? Are we going to have something similar to what we had in the previous case, like line passing through the origin, plane passing through the origin, and so on. So, that is what we are going to look at in the next lecture. Thank you.